3, 2, 1, 0.
Space exploration is humanity's grandest adventure. We've sent missions to visit all of the planets of the solar system and to gaze deep into distant galaxies.
But how do we choose which missions go into space? Only a handful are launched every decade. And for everyone that flies, dozens are left on the drawing board.
This month on The Sky at Night, we're looking at the selection of the European Space Agency's next mission.
5 finalists are now waiting to hear who will get the final spot on board ESA's new rocket.
I do feel a bit nervous. I slept well but woke up ridiculously early.
2 of those teams are from the UK.
Yeah, checking my phone throughout to see if emails will come in, but I've not heard any specific news yet.
And before we reveal the victor, we'll be finding out how they choose which mission will go into space and which simply won't fly. Welcome to The Sky at Night. This is the headquarters of the European Space Agency in Paris, and right now it's hosting a meeting of the Science Programme Committee, the representatives of the 22 member states who have to decide what ESA's next mission will be. ESA is building a new rocket that can carry 2 scientific probes to space. One of these missions has already been selected, and now teams from all over Europe are fighting for the other spot. It will be called an F-class mission. And although the F stands for fast, the mission itself won't launch until 2028. The agency received 23 proposals covering everything from exploring an asteroid to high-energy astrophysics. Each one could transform our view of the universe. They can only pick one. And by lunchtime today, we think we'll have a winner.
This will be the first F-class mission that ESA has announced. They're designed to be smaller, lighter and cheaper than their usual missions, to test innovative ideas and different concepts. Now, we say cheap. This mission is due to cost around 150 million euros. And it has to meet some pretty tight specifications too, including weighing less than 1,000 kilograms. If it meets those requirements, ESA will cover the costs of building the spacecraft and launching it on an Ariane rocket. And although ESA doesn't know which mission they'll launch yet, they do know where the spacecraft will be positioned, at a very specific point in space. As we all know, the Earth goes around the Sun in what is pretty close to a circular orbit. But around this orbit, there are some very interesting locations. They're called Lagrange points. Lagrange points occur because of the way the forces of gravity and orbiting bodies interact. Anything that finds itself in one of these locations will stay there in a fixed position relative to the Earth as they all go around the Sun. Let's start with Lagrange point 1. That sits in here, about 1.5 million kilometers away from the Earth. Now, this is the ideal position for a solar observatory because it has an uninterrupted view of the Sun as the Earth orbits the Sun. Next, we have Lagrange point 4 and Lagrange point 5. They sit at an angle of 60 degrees ahead of the Earth and behind the Earth. Despite being millions of kilometers away from the Sun and Earth, objects here will stay in a fixed position relative to the Earth as it orbits the Sun. Next, we have L3, that sits all the way over here on the other side of the Sun. It is permanently out of view of the Earth and a long, long way away from the Earth, so we don't do much out here. But that brings me to L2. This point sits 1.5 million kilometers away from the Earth, and it has unobscured views of deep, dark space. It's unobscured by the Earth, It's unobscured by the sun and any of the inner planets. And it's at this location that ESA wants to put its first F-class mission. Lagrange Point 2 is a perfect place to study the wonders of deep space. And this F-class mission won't be alone on its journey. It will be piggybacking on another mission, sharing the same rocket. The aerial Exoplanet Atmospheres mission is already being planned at University College London. Its principal investigator is Professor Giovanna Tinetti. Giovanni, we're here to talk about your latest mission, Ariel. But before that, is it weird having an interloper, someone piggybacking on your rocket?
Well, it's not weird, it's actually fantastic. I'm really delighted about that idea because you see, we were having all these big rockets just for ourselves and a lot of empty space. And so finally we can fill this empty space with a great mission. So I'm looking forward to the selection of that mission.
So now let's focus a bit more on Ariel itself. What is Ariel designed to do?
Here is going to look at the atmospheric composition and weather for about 1,000 planets in our own galaxy. So we're very excited about that.
But how's it going to work? How's it going to measure these exoplanet atmospheres?
Maggie, if I can ask you to hold this up. Okay, this lamp will be the light from the star.
Okay.
And typically, the star has a planet that is orbiting around it. When the planet is passing in front of the star, they're basically masking some of the light. And when that happens, then we can work out how big is the planet compared to the star, which is great.
Yes.
But we want to do even more. And that's where Ariel comes in.
To measure the different gases in the atmosphere of these distant worlds, Ariel will use an instrument called a spectrograph.
What we'll do with the spectrograph is to look at the light from the star and split the light into colors or wavelengths.
Which is what we see here.
Exactly.
So this is the spectrum of the star.
And then we wait for the planet to pass in front of the star. And when that happens, the planet has an atmosphere with some molecules, and each molecule will absorb a different color in a different way. And, what is quite incredible is that every molecule, every atom has its own unique signature. And that's why we can find out then what is the composition, what is the chemistry of that planet.
Yeah, if you see the same fingerprint of a chemical that we've measured here on Earth in that spectrum, you'll know that that chemical exists in that atmosphere.
Absolutely.
So how long until we get those first results?
So both Ariel and the F mission will be launched in 2028, and then we need to wait about 6 months before they really arrive where they're supposed to be. And at least in the case of Ariel, we will start to get spectra, and so we will start after about 6 months after launch.
So we're talking ballpark figure 10 years before we start getting results.
It's a long time, I know. But actually, if you talk to the engineers that are really building and doing their hard job of building the spacecraft and the payload, then they will tell you 10 years is not really such a long time.
Well, I think we should put a date in the calendar for 10 years' time so we can come back and speak to you and find out about the amazing results Ariel's discovered.
I look forward to it.
It was only last year that ESA invited scientists to pitch their ideas for a space mission to launch in the rocket alongside Ariel. It was a galvanizing call. 23 proposals from all over Europe were submitted, each proposing different areas of outer space to explore. Following an intensive selection process, these have been whittled down to 5 finalists. And 2 of them originate from this unlikely-looking British space centre, deep in the Surrey countryside. We asked Lucy Green to meet the teams.
This is the Mullard Space Science Laboratory, or MSSL to its friends. It's a department of UCL, and for over 50 years it has been at the cutting edge of space science.
I've been working at MSSL for over 15 years, and now 2 of my colleagues are in with a chance to launch their ideas into space. The first team is led by Professor Geraint Jones. His mission is called the Comet Interceptor.
Hi Lucy.
Congratulations on being shortlisted.
Thank you, yeah.
Tell me about Comet Interceptor and what the aims are for the mission.
Okay, as its title suggests, we want to go to a comet, but unlike previous missions, we want to go to a comet that we don't know about yet, so one that's coming in towards the Sun for the very first time.
We visited comets before, so why is it so important that we visit another one?
So from previous comet missions, we've learnt a huge amount. So Giotto to Halley, Rosetta to Churyumov-Gerasimenko. So there have been big advances in our understanding, but the comets that have been visited by spacecraft up to now have all been past the Sun many times. Each time they pass close to the Sun, the ices on the surface get heated, they change, and they also get covered in this layer of dust that falls back down onto the nucleus. So we like to see a pristine one coming in from the outer solar system for the very first time.
But why is it so important for you to get to a pristine comet that hasn't had any of this processing? What does it tell us?
So the expectation is that if we can visit one of these objects that hasn't been processed, so one that was around when the protoplanetary disk was here before the planets were formed, but was ejected out of the solar system into what's known as the Oort cloud, this huge cloud of icy objects stretching all the way out to roughly halfway to the nearest star. If we can visit one of those objects, we'll truly see what the original material was like when the planets were being formed.
But getting a good view of a comet is going to take some clever manoeuvring and camera work. PhD student George Bryden is working on this.
Now, you've been involved in the mission since the start. How is the spacecraft going to work?
So the spacecraft sits at L2 while telescopes search for a suitable comet, and then once one's found, it'll head off and intercept it. When it reaches the comet a few days before the flyby, it splits into separate spacecraft. They pass by the comet, but they take slightly different paths, so they get a different view. The advantage of this is that because you've got spacecraft from different points, you're able to learn more about the structure of the comet.
And what data will be collected on these flybys?
Particular interest, I think, is the large number of cameras on board these spacecraft. And so the blue spacecraft that gets close actually has a camera on board that's able to scan the whole sky.
Similar in a way to this commercial 360-degree camera we have here, so we'll have several snapshots passing through the comet. Using those and the data from the other cameras as well, we'll be able to reconstruct in 3D the nucleus itself and also the gas and dust jets coming off it. So if we get selected and we gather the data, then you can imagine putting on a VR helmet and actually looking down towards the nucleus and see the gas and the dust coming off this object, which is boiling away for the first time after being formed billions of years ago.
And how are you feeling? The decision is imminent?
Nervous. Yeah, if we're not selected, it will of course be disappointing, but we have a mission concept which I'm sure we'll be proposing again in the future.
Well, fingers crossed.
Thank you.
Thank you.
The atmosphere here is tense, as situated down the hall from the Comet Interceptor team sits the competing British mission that's amongst the final 5 on the shortlist. A mission called Dubai, led by Professor Rob Wicks. Dubai plans to study how energy is transferred out in the vacuum of space.
The big question we're trying to answer is, how does heat travel around in outer space and in the universe? So here in the atmosphere, if I lit a candle over here and it got warmer where you are, that heat has got to you through conduction and convection, and that is molecules bumping into each other in the air. In space, that doesn't happen. It's a vacuum. Collisions between electrons and protons or other bits of the gas don't happen very often. So something else has to pass that energy from electron to electron to transfer the heat from here to there.
How does the Dubai mission help us with that question?
So this is an electron detector that you would typically use on a space mission. And here is a tiny little gap in this detector, and an electron can enter there. And then I can open this in here. We can apply an electric field in this instrument to this sphere, and that will then deflect an electron when it comes in, and the electron will be bent down until it hits a detector down here on this plate. And that tells you then about the properties of the electrons. It's very challenging to do this measurement because the electrons are so light.
So you've got your electron measurements, and then you need to join the dots with the other data that you're collecting from the spacecraft to understand what's heating the plasma.
So what we're going to measure is simultaneously the electrons themselves, the magnetic fields and the electric fields in the plasma. So if I deposit a lot of energy in one place, the electrons over here get hot. What they also do is they make electric fields and they make magnetic fields. the mission is to look for a small population of electrons that are going a bit faster or a bit slower than they should be. And at the same time, we'll look for a little wave in the magnetic field and a little wave in the electric fields. If we see those things at the same time, we can say that wave has scattered or collided with those electrons and caused them to be moved around.
The decision's not far off now. Are you feeling nervous?
A little bit, yeah. It's actually a lot like waiting for your A-level results. Daniel and I worked together very closely with more than 120 people across Europe to put this proposal together. And so no matter what happens tomorrow, I'm happy with what we've done. I think we've done ourselves proud.
Here in Paris, whilst the committee is working hard to make a final decision, there's nothing anyone can do but wait. ESA's science programme costs each of us €1 a year. It's not much, and we can't fund everything, so hard decisions have to be made. And 2 British suggestions illustrate the diversity of ideas that's out there. You don't get much more different, after all, between a fundamental physics mission and a trip to a comet. So how do you choose? How do you pick the one mission with the star quality to succeed? To find out, I sat down with Dr. Fabio Favata, head of ESA's Strategy, Planning and Coordination Office.
The one founding principle of the ESA science program is that all of our science choices, science priorities, science selections are done by a peer review committee, by a committee of
scientists. By other scientists?
By other scientists that don't work for ESA. They are selected from the community for their, of course, seniority, for their competence, and they make the final scientific selection.
Yeah, but how do you pick from such a diverse set of options? You could go to Mars, or look at an asteroid, or study the high-energy universe. Those don't feel like the same kind of thing. How do you compare such different missions?
The proposals that make it on the final shortlist usually are also good. They all deserve implementation. So it's a very frustrating activity for the members of the peer review committee. Yet it's a choice that we have to make because of the resource limitations. We can only afford to fly one mission at the current time.
Well, let's talk about this FAST mission. This didn't exist a couple of years ago, the idea that you'd fly this mission. Can you tell us how that idea came about?
One was the fact that the European rocket launcher program is evolving. Ariane 6 is more powerful than the previous option, and so we've been designing missions for a certain size, and now we discovered that we can carry more. So we said, can we implement fast a smaller mission that allows us to take benefit of this?
So there's a meeting downstairs to make this decision. What do you think will come out of it?
I don't know. All I can tell you is that the leading contenders are so good that there certainly will be a mission that I'm sure will be exciting, and I will be happy to discuss whatever choice will be in the future.
We'll come back and talk to you when we know what the mission's going to be.
It will be a great pleasure.
Luckily, you don't need to be selected for a space mission to gaze out into the night sky. This month, we're going to observe one of its most spectacular sights, Jupiter. Jupiter is currently very low in the UK sky. In fact, it's almost as low as you can possibly get in the sky itself. Now that means the observational window for us is pretty short. But if you've got a telescope and use a bit of magnification, you can see plenty of detail on Jupiter's disk. Now the skies are a bit cloudy at the moment, but hopefully we will get some clear gaps where I can see Jupiter. And if it does appear, I'm going to grab it with it's a 14-inch telescope. You don't really need a massive telescope to do this, but I want to get in nice and close so we get a good picture of it. And I've got a high frame rate camera. I'm also using an infrared filter, and that helps to steady the image. What remains is for us to wait and hope that the cloud gaps come over in time. Jupiter's atmosphere appears as segregated bands of gas, so we'll be looking out for belts on its disk. But viewing conditions are far from ideal. I can see Jupiter, so we have got a gap in the clouds. First thing you notice with Jupiter is you get a disk which looks squashed because it's a fast rotating gas planet, so it expands at the equator and it looks squashed at the poles. But you can see that Jupiter's definitely banded. As the planet rotates, you get these vicious jet streams basically dragging material around, creating this banding effect. But we have got something which is really good. Another sight to behold is the 4 moons that orbit the planet: Io, Europa, Ganymede and Callisto. Tonight we hope to observe the transit of Jupiter's largest moon. I can see Ganymede very close to the edge of Jupiter. It's about to just head off Jupiter as it ends the transit. Now a bit later on, the shadow of Ganymede will start to cross the disk as well. So that will give us a Ganymede shadow transit, and that's actually a much easier thing to see because it's a dark shadow, it's very large, and it stands out really well against Jupiter's bright disk. Unfortunately, clouds stop me from observing the shadow transit.
It's gone again.
But what is it that transits can tell us? As Ganymede or its shadow passes across Jupiter's disk, so a tiny amount of light is blocked from the planet, and it's possible to measure that minute dimming of Jupiter and work out that there's something in orbit around it. This is similar to a method used to find exoplanets, by observing a distant star and looking out for a reduction in light. And if that dimming happens for a fixed length of time at regular intervals, then it's probably due to a planet. As we know, the Ariel mission will be studying exoplanets. And to do this accurately, the team at UCL will need to know the precise transit time of the exoplanets across their stars. And this is where amateurs can get involved, because Ariel is planning to bring together individuals with all different sizes of telescopes to create a network dedicated to the observing of exoplanet transits. Now, these observations will help refine the data about the planets and their orbits, paving the way for Ariel to characterize their atmospheres. More details of how to get involved can be found on the Ariel mission website.
It's decision day. Which one of the missions will be chosen to be launched on ESA's latest rocket? The leaders of both UK teams are not in Paris. They're actually in the same presentation, in the same room at UCL, anxiously waiting for news.
A little nervous. I did get to sleep last night, but I woke up incredibly early. Rob and Daniel are in the room here with me as well, so we've got a day of listening to project talks today. Hopefully at some point we'll hear the news.
It's a nail-biting morning, but at 2 o'clock, the moment they've been waiting for finally arrives.
Just received an email from ESA confirming that Comet Interceptor has been recommended for further study, so quite a relief. If all goes well from here on, then it'll keep us busy for between 12 and 15 years into the future. So should keep me busy all the way to retirement, I think.
In Paris, I caught up with Chris Lee, the UK's man on the committee. So you're just out from the meeting. We hear a decision has been made. What happened?
Right, so Comet Interceptor has been selected.
Oh, that's good news. And that's a British-led mission as well.
What we really wanted with the F mission was something that was innovative, something that put technology together in really interesting ways. And the thing that I think we all agreed in the meeting was that Comet Interceptor came up with a really imaginative approach of using existing solutions for instrumentation and spacecraft, but put together in a package we'd never seen before, and which will be very fast. We have to move quickly because we already have a mission that's going to go. It's the Ariel program. And so it's the ride that joins the Ariel initiative, and the clock is ticking already.
What are the next stages that this mission will go through? It's got approval today. What happens next?
Okay, so first of all, it was a genuine competition. So it's won because of science merit. But what we now need is a detailed study to work out exactly what the technology needs to be, what the instrument needs to offer, what the spacecraft needs to address, and then we will get a costed proposal.
Okay.
And it's at that point the mission is what we call formally adopted, and that will be around November 2020.
What does that mean for the UK Space Agency in the UK?
Well, first of all, it means we have to pay for it. So the thing that we have to try and emphasise to people is that our investment in ESA pays for the spacecraft, pays for the launch, pays for the operations, but we actually pay for the instruments ourselves through the national programme. So it's a partnership.
Cameras and the things that will do the science.
Absolutely. So yes, it's led by the UK, but we have to recognise it's a strong European project.
So these are European missions, but both Ariel and Comet Interceptor now are UK-led missions. Why do these missions get people excited?
Well, I think it's important to realise that we're a UK space agency for science as well as for industry and economics. So from our point of view, it's great to have a motivational programme from a space science perspective, because we are living in a golden age of European space science, and we can show that the UK is not only being involved in the building of the spacecraft, but actually contributing to the reason you're flying it in the first place.
Well, it's a good story, and I hope we'll come back to it again and again in the years leading up to and after launch. Chris, thank you very much.
Thanks, Chris.
Geraint can't wait to share the exciting news with his mission co-leader, Dr. Colin Snodgrass, from the University of Edinburgh.
Hi, Colin.
Hi.
I guess you got the same email as I just did.
Yes, very good email to get.
Yeah.
Exciting news.
Huge relief. So, sorry we're not in the same place to share the news, but somewhere out there beyond the orbit of Pluto, there's something approaching the Sun, and we don't know about it yet, but hopefully we'll get to see it. Okay, I'll speak to you again later. Thanks for all your help with this. Yeah, thanks a lot. See you.
All right.
Bye.
Bye.
Congratulations.
Thanks very much.
Very well deserved.
Well,
The other team has taken the news graciously. But ESA's announcement wasn't all bad news for the Dubai mission.
So I've just received an email saying that the first choice mission is Comet Interceptor, and the second choice, and a backup if Comet Interceptor runs into trouble, is Dubai, my mission. So, fantastic result. Obviously, we'd rather be number one, but if you can't be number one, you better be number two, and that's what we've done. So, a great result for UCL, a great result for Mars Space Science Laboratory, and I could be slightly happier, but I'm not unhappy.
Considering that we started from scratch last year with a completely new mission concept, that's very exciting, very good news for us. Of course, if ESA needs us at any point, we will be ready. We won't throw away the mission concept, and maybe we find another home for this proposal. But at this point, it's really just a great result. We're very happy.
It's been an exciting day for UK space science. In 2028, ESA will propel 2 British scientific probes out beyond Earth's orbit to make discoveries about exoplanets and the origins of the solar system.
Congratulations to the Comet Interceptor team, and we'll look forward to following their progress on the sky at night as they head towards launch.
That's all we've got time for this month. But do join us again for the next programme, where we'll be finding out about the latest research into exoplanets. Also in the autumn, we'll be holding the Sky at Night question time, where Pete, Chris, myself, and some selected special guests will be answering your questions in front of a studio audience. So if you've got a question you'd like to put to the team, send it in to skyatnightqt@bbc.co.uk. Until then, good night.
In the meantime, if you have a question about the moon, then your answers may well be available right now in the Sky at Night Book of the Moon, a guide to our nearest neighbour. Next tonight, and very much on terra firma, James May's Cars of the People.